There's still a couple people that are going to be trickling in, but the first couple slides I have are just kind of catch up from this morning section. So if you're watching along at home and you can't see who this is, I'm Lindsay Pino. I introduced myself earlier this morning, but I am a former mentee of Sue's, and now I am working with Dr. Mike McCoss at the University of Washington. So this morning, Sue kind of walked you through the mass spectrometer side of the method, but I think almost everyone in here is hyphenating their mass spectrometry with liquid chromatography. So now we have to spend some time talking about the liquid chromatography because they really work together for getting us good data. I did want to mention to you guys, and I'm going to try to stay tethered over here so that the recordings will be okay for you to use at home. But I wanted to show you guys, if you go to the Skyline website, skyline.ms, you don't have to do this right now, I took screenshots for you, but if you want to play along, that's great. If you hover over this home, it should drop down a menu under home, under software. You'll see, or should see something listed called BiblioSpec. So this is the functionality that lives within the Skyline ecosystem for making spectral libraries. So if you had any questions about what we were talking about this morning as far as making spectral libraries, you'll find a ton of documentation here on the Skyline site. So I wanted to show you in particular one of the functionalities in BiblioSpec. If you look on the right-hand side of that BiblioSpec page, you should see all the BiblioSpec spectral library tools. If you click on blib build, this is actually how Skyline is going to be building those spectral libraries from the search results of your DDA data. So this is where the table that Brendan had showed you this morning, where he showed you all the different DDA search algorithms that you could use to analyze your data, and you can dump those results into Skyline and they'll make your spectral library for you. So that's this table here, and you'll notice Skyline team has already meticulously organized it for you so that it shows you the database search. So if you scroll down, this is a huge long table and it has pretty much every flavor of DDA search algorithm you could possibly be using. It also gives you the ID file extension. Those are the files you need to use to open in Skyline to make that library if you're going to build it from the search result files. So hopefully that helps you out as you're making your own spectral libraries. You notice there's some other tools in here too. If you click on those, you can learn a little bit more about spectral libraries if you wanted to take your knowledge one step farther. But actually, I'm not talking about that this afternoon. I'm talking about retention time, something called IRT, and the types of standards that you can use for retention time. So what I'd like for you as students to get out of this, there's obviously a lot of information in these courses, but if you could check these boxes, I would feel like you walked away with everything I wanted you to get out of it. So I wanted you to kind of see from an applications standpoint what retention time is. I don't want you to just be able to define like, oh, retention time is when a peptide elutes in a liquid. I want you to have an intuition for what retention time is, and I want you to be able to kind of compare and contrast the two major ways of predicting retention time. So one of the ways is I have no prior knowledge. All I know is my peptide sequence, the specific amino acid letters of the peptide. And the other way is you can use standards. In the second half of this 1:30 session, so I'll spend some time introducing you to these concepts, and then Brendan's going to walk you through a step-by-step tutorial of building one of these retention time prediction calculators in Skyline. So first I'm going to be just introducing you to these concepts before we go ahead. So like I had mentioned, Sue taught you this morning how to start putting together this list of peptide sequences. But the other half to LCMS is the LC. So you can't do LCMS without kind of having some idea of liquid chromatography. So I think, looked like most of us in this room are using nano LC. There were a few doing higher flow. Is anyone directly infusing from like a syringe? Is everyone doing some sort of separation? It looks like everyone's doing some sort of separation, so hopefully this is useful for everyone. So very briefly, liquid chromatography is we take our column and we pack it with beads with some sort of stationary phase, and we're going to flow a mobile phase over it, solvents over it. And your lab might call these different things. You might call them solvent A, solvent B, you might call them 1 and 2. You might actually just refer to them as acidified water and acetonitrile. Whatever you're using, you're mixing two solvents together into a gradient that will be flowed over the stationary phase, and then peptides will elute off of your gradient at a specific point in that mixture. So that's the retention time. So you don't have to open up Skyline right now, but later when we start doing some Skyline stuff in the 3 o'clock session, the hands-on Skyline stuff, I wanted to point out that Skyline can show you data with multiple peptides so you can visualize a gradient. And you just do this by using control and selecting what peptides you want to see. And then you can compare all the elution times for multiple peptides in a single file instead of just seeing the one peptide's chromatogram. So how can we predict when a peptide will elute? So one way to predict elution time of a peptide, the retention time of a peptide, is to go in with no knowledge whatsoever besides the specific amino acids. So there's an algorithm from over a decade ago now, I guess, called SSRCalc. And SSRCalc stands for Sequence-Specific Retention Calculator. So all it's actually doing, it's pretty clever. They found specific what they call retention coefficients for each amino acid. And then what they do is just sum all of the different retention coefficients for each amino acid. It's a little bit clever in that it also considers the N-terminal amino acid, because the N-terminal amino acid of your peptide will affect the retention time slightly differently than any other amino acid. So Skyline has built that function straight into the program. So in Skyline, Stu had mentioned you can view in the retention time pane within the Skyline visualization, you can view the SSRCalc score for all of your peptides on the x-axis. If you go in the retention time pane to graph regression score to run, will give you this SSRCalc 3.0 300 angstrom score. So it'll give you the index on one axis, and it'll give you the measured time on your y-axis. So if we blow that up, so now I'm just looking at the retention time pane, and I'm looking at the score to run. I want to orient you and give you a feel for this so that you're pretty comfortable with what this is showing you. So it's showing you an SSRCalc index on the bottom, the score on the bottom. On the y-axis, it's giving you the actual real retention time that you saw that peptide in a run. So you won't get anything on the y if you don't have any runs in there. If you don't see a peptide in a run, you won't have any value for measured retention time. It'll be a 0, and you'll see a bunch of dots right on the x-axis, y of 0. And each of these diamonds is an individual peptide. So you can see in the peptide, if you trace down, you can see its SSRCalc score. And if you trace across, you can see its measured retention time. And notice they're not exactly 1-to-1. The score is not necessarily like a minute's retention time. You're correlating the score to a retention time. And Skyline does that for you because it's so nice. And that's the equation you can see in the top left corner of that pane. That's the regression fit for the score to give you a retention time, predicting from a score the retention time for that peptide. So you notice that the R value, the goodness of fit value here is over 0.9. That's a setting in Skyline that you can change. And that's maybe a little bit more of an advanced thing. I don't know too many people that mess around with lowering this threshold or raising it, so you don't really have to worry besides knowing if you, for some very special experimental reason, needed to change it, you could. So what this looks like, if we blow up the retention times pane, So my peak area is pane down here. I've just drawn straight down because I didn't want to look at it right now. And I'm looking at the chromatogram for all of the peptides in this method. So notice that all of these peaks in my chromatogram pane are labeled with 3 amino acids if they are a unique peptide. There's a special peptide down here in pink that might not be able to see too well, but it has 3 letters and then ... 3 more letters. So that makes it easier to identify because maybe I have another peptide in here that also starts with ELA. So what I can do, and Sue was talking about this too, if you click on one of these dots in the regression pane, the retention time regression view pane, if you click on it, it will take you to that peptide and show you that peptide's chromatogram. So I can see, all of the peptides. I can select all of the peptides in my target pane and it'll show me all of the peptides on that chromatogram. Or I could click one peptide. It'll show me that one peptide highlighted in red in the retention time pane and show me its chromatogram in the chromatogram pane. So I started out nice and showed you a very clean example of an SSRCalc score to run view in the retention time pane. But we can get a little bit crazier with this. So for example here, the projector makes it a little bit tough to see, but hopefully you'll be able to see this in your own screen in Skyline. Some of these dots are blue, and some of these dots are kind of a bright purple lilac color. So if you're able to read the legend up here, the bright purple color is an outlier. So remember I mentioned that this R squared, Skyline sets a default threshold to be 0.9. If you have an outlier, then it will color it and not include it. But like I said, you can change that threshold and view something a little differently. So notice if I include all of these outliers, the fit of that regression goes way down. The goodness of fit goes way down. And also the line itself changes because we're including all of those outliers. So maybe in this case, I would need to go in and click on these peptides, check and make sure they were picked correctly. Maybe they're not even there and I just need to integrate over where I would expect that peptide to be. And then you'll see this pane get updated real time as I'm changing those integration boundaries. Yes?
Are you going to say anything about that horizontal bunch of peptides at the very top?
Oh, across the very top. Would you like to say something, Sue?
Are you going to say something?
I was not.
Okay.
Go ahead.
So one of the reasons I really like this view of the retention times is because you can, again, you look for patterns. And so the first thing that jumped out to me there is that, man, there's a whole bunch of peptides coming out at like 72 minutes. What the heck is going on there? That is not usual. You really should see it fit more towards that regression. And so to me, that means something funny is going on. There might be a large signal coming out in that region of your chromatogram at 70-something minutes. And so if it were me, the first thing I would do is I would politely close, like minimize Skyline and go to whatever raw file viewer I have to see what the tick looks like. And the reason is because I want to see what's happening right there. That's making Skyline think that's a whole bunch of peptides that really aren't ticked, right? Because you shouldn't, it's odd in this type of plot to see vertical peptides all with the same SSRCalc, and it's weird to see ones that are all horizontal. The other thing that you could see if you had a messed up run is if you injected your sample and a bunch of your peptides came out early, you'd see that same horizontal thing, but at like 10-minute mark. And you should really never see something like that. It should be a gradual correlation.
Yep. So Sue was just mentioning, for people listening in at home, Sue was just mentioning at the 70-minute mark, there's a horizontal line of peptides, and that might indicate something's happening at the end of my gradient, that Skyline's thinking, oh, that's where all of my peaks are, when we can tell by looking at this regression pane, in this retention time pane in the regression view, that doesn't look like it's right at all. The other thing I guess I should point out here is I mentioned if the peptide is not picked, it's not measured, we should see a bunch at a y of 0, at a measured time of 0, and we do see that here. Those outliers in purple are sitting right on the x-axis with a y of 0, so we didn't measure them. So thing to take away from this slide is that we can have pretty complex looking regression time regression view panes here, where we have these outliers in purple, the purple dot outliers, and that can change the fit, the regression parameters of the SSRCalc model. So I'm going to change gears a little bit. I wanted to stop and see if there are any questions about SSRCalc and the regression view in the retention time pane.
When you're running maybe complex sample, so what we expect regression, R-square is going down usually?
A complex sample,
yeah,
as long as your peptides that you're targeting are measurable, I wouldn't expect to see the regression to look any worse. It's should be pretty well correlated. The SSRCalc is strictly based on the amino acid sequence of the peptide, so it shouldn't be affected by the matrix. Another question in the back?
So maybe I missed that. So if I want to do this correlation,
Mm-hmm.
I only need to, let's say, have the rest of the peptide running once and I target this, and then I can run this correlation based
It'll
on
automatically run for you. Yeah. As long as you have one run so that it can have some y values, because it's trying to predict the y, right? If it doesn't have any measured times to predict, there's no way you can make a model without any kind of times, measured times. One more question? Yeah.
Is there any coefficient for modifications?
Modifications doesn't change this at all. Each of these points would then be the modified peptide sequence. So this, yes, one more question, SSRCalc.
Do you know if the regression will change based on what your runtime is if you're running a shorter time?
Absolutely, so that is excellent. We have a data set that we will be playing with that this afternoon at 3. So pay attention because you're getting quizzed on this at 3 with a data set that's exactly that. 7 different gradients, how does this change? All right. So switching gears only slightly, a different way to predict retention time, and depending on who you ask, is the better way of predicting retention time is to have an empirical measure of it. So before we were just taking the sequence, so one of the questions was, what if I have a modified peptide? Will that change this? SSRCalc won't do anything differently with a modified, but it could change the retention time, right? If anybody has done some phospho work, isoforms of the same phosphopeptide will elute slightly differently, and SSRCalc can struggle with that a little. So especially in things like that where we're interested in a site-specific modification and really pinpointing the retention time of that, something like IRT is a better solution. So what IRT does is it takes some anchor peptides. So in the slide, the anchor peptides are shown as IRT PEP1 and IRT PEP2 in red. So those are just the chromatograms of these 2 anchor peptides. And then all of our unknown peptides, so peptide X, are represented as some value in between the 2 peptides. So let's walk through an example because that was pretty vague. So in this example, IRT PEP1 elutes first of these 3 peptides, so we'll set that as a 0%. IRT PEP2 elutes last, we set that as 100%. So now we can just calculate the quote-unquote distance between these 2, the amount of time between IRT PEP1 and IRT PEP2. If we divide that and represent it as a percentage, then peptide X elutes at 60%. So now as long as all of the runs going forward, we measure those anchor peptides, we can shift the percentage and know when our unknown peptide is eluting. Any questions about this? Yes?
So if you're using something like PRTC.
Absolutely, yep. You plugged, you work? No? Okay.
Would you do this, I mean obviously it's going to be peptides that fall within
certain peaks of the PRTC and some that don't.
Yep.
You just pick sets and every set will.
You can use all of the standard peptides that are included, the 16 peptides in the PRTC mix, is that correct? 16? 15, sorry.
And PRTC stands for Pierce Retention Time Tolerant Peptides. And
Yeah.
so we just call it PRTC.
Yes. And I will mention in a couple slides some of the various commercial options you have available to you if for some reason you have a grudge against Pierce and don't want to use their retention time standard mix. You can use any number of other commercial mixes. So the concept is the same though, no matter what anchor peptides you're using. If you have multiple IRT peptides, that means you can narrow down that percentage that much better. So if I had another IRT peptide 3 on even farther in my retention time dimension than this 25 value, then you can imagine if I have another unknown there, now I can pinpoint that even further. The way we view retention time with IRT calculated retention times is very similar in Skyline, still in that retention time pane, the retention time view. Now we can visualize, instead of the SSRCalc score, we can just change what we're viewing to the IRT calculator score. And Brendan, right after this, will be walking you through how can I set up this calculator with a set of anchor peptides, a list of anchor peptides, and I want to make this calculator. So one of the things that you might notice here is that the axes are very similar. On the x-axis is just a score that is predicted by the calculator, and on the y-axis is the measured retention time again. You may also notice in the equation up in the upper left corner, this is a much better model fit using these empirical times versus using the SSRCalc, which just uses the amino acid sequence. And this has been shown to be true. So now I'm just showing you on the left and on the right. On the left, the SSRCalc, like we were looking at before. And on the right, the IRT calculated views. So you may notice, like I just said, up in the upper left corner, if we're comparing these two regression values, the goodness of fit on the right is 0.9991, so pretty decent fit. And when the method for IRT-based calculation of retention time was published, they did a comparison with SSRCalc, and they showed that when you can use an empirically based IRT calculator, you'll get much better predicted retention times than if you just use the sequence. This goes especially true if you have modifications, and especially isoforms, where the sequence is not super different, but the retention times can either co-elute or elute in different places of the gradient. So I'm going to change gears and just about ready to pass it off to Brendan, but I wanted to take questions now that I've shown you two different ways. Comfortable so far? Yes?
So this requires defining the IRT scores in a previous run and then the correlation will be performed for all future runs?
You have to do at least one run with the IRTs in the matrix that you're using. So that's an important thing I didn't mention. If you're going to be changing between matrices for some reason, maybe you're doing tissue and plasma, or something like that. Those matrices are very different, and that will affect things like this IRT. And if you change the gradient, that's another thing. You need to run another of these to update your calculator with the IRTs, but you need to do one run. You can just look for the IRTs if you want to set up the calculator initially. There are some databases available now if you're using databases to source some of your hypotheses for what peptides you want to target that are starting to include an IRT value. So remember, as long as the anchor peptides are the same, which if you're using a commercial, like one student mentioned PRTCs, if you're using a commercial set of anchor peptides, then any other lab in the world using those anchor peptides, you can steal their IRT value for your peptide. So very useful, but Brendan will walk you through specifics.
Just to kind of expand on that
Yeah.
just a little bit more. For example, our biggest problem is the columns that we use, and to switch those, is that we have to run it on a new column.
You would run this again on your new column, and I have an example of what that might look like if you switch columns. The question was when we change out our column, when our column ages, and we put on a new column, now all of our retention times shift. So IRT is a great way to commute the old in quotes retention time to the new column, because you can correlate, like they showed on this slide, you can correlate across runs as long as those anchor peptides are still being measured on the new column. You can update the calculator. All right, so like I keep mentioning, Brendan will be down. I wanted to just show you some of the different retention time standards that you can choose from. So we mentioned the commercial Pierce standard, which is an exogenous commercial standard. There's also Sigma Aldrich has one, Biognosis has one. I think Cambridge Isotope either has published or will be soon publishing on one. So the exogenous standards, if you can afford them for your project, are great because they're extremely reliable. However, you have to be able to afford them because remember, you're supposed to spike these into all of your samples in order to use them the way they are intended to be used. So if that's not an option for you for your project, maybe you're the only one doing proteomics in your group, that's okay. You can still use experiment-specific endogenous standards. If there's just some protein, some peptide that you're going to see everywhere all the time in roughly the same amounts in all of your samples, you can use those to be anchor peptides. So I know someone who has used human keratin for one of their standards because they was getting in all their samples anyway. So they use that to be one of their anchors. So you can consider for your specific experiment something that you might always see no matter what, and use that to be one of your anchors. But remember, it just has to be in all your samples, and the retention time needs to be pretty well established. So the point of doing these, like we just mentioned with the column, as a column ages over time, the retention time will start to drift. After the first 4 runs, you may notice a large retention time drift for a column that has never been exposed to peptides, never conditioned to peptides before. So a totally fresh, brand new column may start off with a retention time of say like 27 minutes for your standard peptide number 1. And then as the column starts to condition, the retention time might start drifting down. If you go to change your peptide, it might shoot back up again. So this is not actually a red underlined word zoom. That's the new retention time for if we have a new column, that same peptide will shoot right back up. So this is a pretty wide drift of 10 minutes. So if I didn't have standards in there to see that the retention time changed by 10 minutes, I could totally mispick that peak because I'm looking 10 minutes earlier in my gradient. So just the quick conclusions, peptide retention time has very little to do with the mass spectrometer instrument itself. It's the liquid chromatography section that, as a community, the LC-MS proteomics community doesn't want to think a lot about LC and retention time, but it's extremely important for your data quality. We can use SSRCalc to just use the amino acid sequence of our peptide targets, but even better is if we can use IRT with either an exogenous commercial kit or with endogenous to our experiment peptides. And Skyline supports both of these. So in the slides, when you get the slide deck, I've just got bonus information if you are an A+ student and really want to go impress your lab, but I will turn it over to Brendan to show you how to make an IRT calculator in Skyline. Any questions while I come down and get set up? Took most of